Hello, today we are continuing our problem solving on the topics of the laws of Earth's flow, and we will consider the following question. At what height above the Earth's surface is the acceleration of free fall equal to 1/4 of the acceleration at the surface? So we need to find a certain altitude at which the acceleration is 1/4 of the acceleration at the surface of the Earth. Let's denote the acceleration at the Earth's surface as g and the acceleration at the altitude as g. What can be done in solving such a problem? In this case, of course, we have certain constants, such as the radius of the Earth, or we can express the given height through the radius of the Earth. There are two ways to solve the problem. Let's look at the problem considering that we denote the radius of the Earth by the letter r. So what do we have in hand? You and I already have ready relations between two quantities, i.e. acceleration at altitude and acceleration at the Earth's surface. For each of these, let's write down the corresponding formula. So what is the acceleration at any altitude? Well, as we know, it's a quantity that will be determined depending on the altitude of the object itself. All other parameters, such as the gravitational constant, the mass of the Earth, the radius of the Earth, are in this case unchanged values. Further, g0, which is the acceleration at the surface of the Earth, is going to look in a similar way, but in this case, just without the altitude. And now our task is to substitute these formulas into the original relationship we have at the very beginning. So g is a gm divided by r plus h squared, and here we have gm divided by r squared. And the quotient is 1/4, which we put in front of the value of g0. So what do we get with you here? We see that we can reduce the mass of the Earth and the gravitational constant, and for convenience we can invert this equation and extract the square root from it. We see that here we have a square remaining. Here we also have a square and plus 4. Very convenient for extracting the square root. Then we get r plus h on the left side. And on the right side we have two r's. And then from here you and I can see that h will be equal to r. So if we go up to an altitude equal to the radius of the Earth, 4 times the length, that is the answer to this problem. Now the second question, what is the acceleration of the Earth's gravity at a distance from the center of the Earth equal to the radius of the Moon's orbit? That is, how much acceleration will the Earth generate in the area where we have the Moon? Let's rephrase this question this way. We will calculate g for a given point based on some constants. What do we know? We know that the mass of the Earth, which is needed for this calculation, is about 6 times 10 to the 24th power of a kilogram. And we also know that the radius of the Moon's orbit is approximately 384,000 kilometers. To calculate the problem, we will need to convert all the data into C. We already have the mass in kilograms in system units. All that's left to do is to convert the radius. Here we get then 384 by 10 to the 6th degree of meters. Let's write down the answer in this format. For simplicity of consideration of the task, let's depict in the figure how this situation will look like. Here we have Earth, and at a distance r from it is the Moon. We consider this distance as in this case, the distance between the centers of the Earth and the Moon. Now our task is to find at this point what acceleration of free fall will be created by the planet Earth. To do this, we'll use a well-known formula that we know, gm divided by r squared. So we show you that the acceleration of free fall can be calculated at any point, at certain distances. The main thing is that you know the distance at which you are looking for this acceleration, and the main thing is that this point is not inside the Earth. Again, I remind you that there is a specific methodology for points inside the Earth. So g will then be equal to 6.67 by 10 to the minus 11th power multiplied by 6 by 10 to the 24th power, divided by the square of that distance. And everything is squared. So after doing the calculations, you and I get to approximately 0.3 thousandths of a meter per second squared. The value is very small, of course, due to the enormous distance, quite a large distance from the Earth. But nevertheless, once again, due to the larger masses, the force between the Moon and the Earth is of sufficient importance to keep the Moon around the Earth, to keep it rotating in its orbit. That concludes our lesson. Goodbye.